Okay, so now let's take a look at a coding example where we implement some linear programming and quadratic programming optimization problems. Again, if you haven't already done so, open up this deep project that we're working on. And this time we're going to look at the second notebook called linear programming. And in this notebook, we're going to learn to inspect a linear programming problem and then to solve this using Scipy, a package for scientific programming, and in particular, the optimize and linpro, which is the linear programming function. And then we'll also take a look at a more realistic example, not just with a lot of mathematical equations, but how we can actually translate a real-life example into the mathematical formulation of it. Let's go into it right away. First, we want to inspect the problem. If you remember from our workflow, the first step usually will start by inspecting the problem. Then before we commit to it, we'll then think about the approach, the strategy. Then once we've decided on the approach to take, after that, we'll then commit to running the optimization problem. So let's consider this linear programming problem. We know linear because the objective function is a linear function. And then with respect to x1 and x2, the design variables and also some linear constraints. So we have here some inequality constraints and one equality constraints. Now, to visualize it and also solve it later on, we want to first convert it to the standard form we have learned from our first lesson, where the inequality constraints would be less than or equal to 0, and the equality constraint will be equal to 0. And this is also the standard form that can be recognized by Scipy. And once you've rearranged it to a standard form, you may use a piece of paper to write down how it should look like in that form. Once you've done that, feel free to click the Show It button here to see the answers. Okay, so now assuming you've already arranged it into standard form, you can click on this Show It button and see how we can arrange it in the standard form. Again, we have to first define the x1, x2 arrays, and then create a mesh grid of the two-dimensional array, and then define our objective function. The inequality and equality constraints now become something like this. So we have g1 equals to x1 plus x2 minus 20. We're essentially moving the 20 over to the other side, so it becomes 0 on the right-hand side. For g3, for example, minus x1 plus 2x2 greater than or equals to minus 2, what we want to do is that we want to move the negative 2 to the left-hand side and then multiply everything by negative 1 to flip the sign from a greater than or equal to a less than or equal to sign. So it becomes something like g3 equals x1 minus 2 times x2 minus 2. So this would be what a standard form g3 constraint look like. Now you can also run this code block so it will execute. Now we have all of these definitions created. We are now ready to visualize the linear programming problem. As with before, we are going to use Plotly, and the way we visualize it would be following a 3-step procedure where we first create a figure, then we update our layout according to how we want to represent the visualization. Any aesthetic layout formatting, we can also do it in this step here. Then we'll create our contour plot for the objective function. Here we're trying to visualize it in 2D, that's why we are using a contour plot. So we specify x was x1 range and y as well. We specify to our objective function. And then we use a function pattern that is a very handy way of combining two kinds of things. We want to create a contour plot for each of our constraints, right? We have G1, G2, G3, and H. We can actually zip this together. So G1, G2, G3, and H, they are basically the actual constraint values. And we also have the names of them. And then for each of this, G1 and G1 here, G2 and G2 here, G3 and G3 here, and finally H and H over here. We then perform some operation in this for loop here. So for set being the constraint and the name for the constraint, we want to create a contour plot. And we specify set as the current set that we've looped to. If it was the first iteration, then it would be G1. The name would be G1 here. And we can specify it here the contour to be a constraint type with an operation less than or equal to if the name is not H. So for all of the G1, G2, G3, the operation will be a less than or equal to operation. If it was H, meaning that it is an equality constraint, then we want to say operation equals to just the equal sign. So this is how we can, in a clearer way, say that we want to perform this operation for the same kinds of objects. And once we've done that, we can add all of the plot elements to the figure. And you can see this is what our plot looks like. The background contour is our objective function. And then we have G1 constraint here, shaded in orange, and G2 constraint here, shaded in green, and G3 shaded in purple, and finally equality constraint, which is the orange line here. Now try and see if you can answer these questions and select the appropriate answer from the code. Then once you've gone through this part, we can move on to the second part where we are actually going to solve the problem. So running our very first optimization implementation. To solve this linear programming problem, we can use Scipy's linprog function. Scipy defines a linear programming problem in this form, so it's a little bit different to our standard form. It says that basically a upper bound matrix AUB times X less than or equal to another vector B upper bound, and then A equality matrix times X equals to B equality vector for the equality constraint, and X will be bounded by L and U appropriately. So here, the function signature will be something like this, linear prog. C would be our objective vector in here, AUB, BUB, AEQ, BQ, and the bounds, which are the L and U. So how do we convert it in this form? For example, if we look at the argument C, it corresponds to the coefficients of x1 and x2 in the objective function. And because we have a maximization problem, coefficients will have to be multiplied by -1. So we have C equals -1 and -2. And again, see if you can write out the rest of the arguments. You basically have to find a way to express AUB and BUB, AEQ, BQ, and the bounds. And you can pause the video as well, and we'll see later on how this is actually done. Okay, now assuming you have already come up with the representation, let's click the Show It button. The objective function is -1, -2, as we said earlier. The left-hand side of the inequality constraints, we actually have to represent it in such a way because we have 3 inequality constraints, right? So each list within this parent list is basically a row factor in the matrix. So 2 times 2x1 times 1x2, which will correspond to our constraint over here. So 2x1 plus 1x2 would be less than or equal to 20. So 20 would be the right-hand side of that BUB factor in here. So RHS inequality, which is the right-hand side of the inequality constraint, will be 20. And similarly for the second constraint, -4x1 plus 5x2 would be less than or equal to 10. So that's how you can represent the inequality constraints. And similarly for the equality constraint, we have -1x1 times 5x2 equal to 15. So that's how you can represent it in the way that Scipy understands. For our bounds, because we want x1 and x2 to be greater than or equal to 0, so it has to be positive, we can do this by saying that the lower bound of x1 is 0, the upper bound being infinity, so we can use np.infinity for that so that it understands it's infinite. And similarly for x2 as well, so this is how we can define the bounds. So once we've defined all of these variables, we can supply it to linprog, which is what we've imported from here. C is the objective that we've defined in here. AUB is the left-hand side of the inequality constraint. BUB is the right-hand side of the inequality, and so on for the other variables. Then once you run this code block, you should see something that outputs like this. Optimization terminated successfully, meaning that an optimization solution has been found. The function value would be something like -16.81, and the value of x1 would be 7.727, and x2 would be 4.54 in here. Now, it also shows you all of the residuals and marginal values for your constraints here so that you can verify if the constraints have been satisfied or not. And to extract this result, we can use opt.x from our variable here. We've defined opt as the result of the running of the function linproc. So with the result here, we can then visualize it just like how we did previously by adding a scatter plot of opt.x for the x coordinate. We want to index it at the 0th position, and for the y, we want to index it at the 1st position in here. And you can see this is the result, and it does make sense because it is in a feasible region touching just one constraint, and because we are maximizing in this problem, so naturally it has to be a point lying on this line which have the reddest color or which have the highest value in this optimal objective value. Now again, we have some questions here for you. Feel free to have a think about it and then answer it in our upcoming quiz as well. Now, let's take a look at a more realistic example. This is also going to be your first example in translating a real-life optimization problem in mathematical terms. So suppose you are creating a custom mix of nutritional supplements. Nowadays, this is quite a common thing to do. You can go online and search for something like this and mix and match your cocktail of nutritional supplement. Each ingredient A, B, C here has its own cost, and it contributes different amounts of vitamin A and C and calcium. The final mix has to meet a specific daily nutrient target, but you want to keep the cost as low as possible. Now the question is, how much of each ingredient should you include? In here we have the requirements. So we want to have at least 0.7 to 1 milligram of vitamin A and 80 to 120 milligrams of vitamin C. And for calcium, we need 1,000 to 1,300 milligrams of it. Now we want to choose different amounts of A, B, and C while keeping the cost as low as possible and the combination of them satisfying these constraints over here. To solve this question, we first want to write it in the standard form. Our objective is the cost, right? We want to minimize the cost, so we can say that F is 0.06 times A, which is the amount of it, and 0.03 times B plus 0.01 times C, the amount of ingredient C. And the constraints we can specify it like this. For vitamin A, for example, from ingredient A, it provides 1.5 milligram, so we want to times it by 1.5 plus 0.2, which is the amount of vitamin A in ingredient B, plus that of ingredient C, which is actually just 0. And this total amount of vitamin A must be from 0.7 to 1.0. And similarly, we can do the same thing, looking at this column for vitamin C and looking at this column for calcium, to write out our constraints here. However, note that Scipy does not accept two-sided constraints, so we'll need to convert each of them into two one-sided constraints. So for example, for the first vitamin A constraint, 1.5 XA plus 0.2 XB must be less than or equal to 1 and greater than or equal to 0.7. If we look at just the left-hand side of it, we can say that 0.7 must be less than or equal to the center part here, and we can then use our arithmetic operation to convert it into the other side, so we multiply it by -1. Then on the right-hand side, we can just take it as it is, 1.5 XA plus 0.2 XB less than or equal to 1.0, and we can just move the 1.0 to the left-hand side so it conforms to the standard form. So now you can try as well converting the rest of the constraints into this one-sided constraints and use the linproc function we have earlier to see what the solution would be. Okay, so let's see what we've done in here. So in this code block, we have defined all of our constraint functions, all of our objective functions, coefficients, and in here, we're trying to define all of the left-hand side of the inequality constraints and then the right-hand side of the inequality constraints. And for the lower bound of the vitamin A requirement, we need to multiply it by -1. Similarly for vitamin C and calcium. So that's why we have done it here like this, -n for n in NA, NA being this list over here. Once we've got all of these variables defined, we can then run our optimization, putting all of the variables we've defined earlier into this function, and you should see the result as something like this. Now, because this problem is three-dimensional, because we have three design variables, xa, xb, and xc, representing the amount of each of the ingredient, we can't really visualize it directly on a 2D contour plot. What we can do instead is that we can fix one of the variables and plot the other two. Let's begin by fixing xc to its optimal value, and we can then plot the contours of the objective function and the constraints in the xa, xb design space. So here we say we fix xc to the opt.x in the second position, which is the value corresponding to xc. Then we do the same thing, define the constraints, objective function, create the figure, define the layout, and then plot the objective function contours, plot the constraint contours, and finally plot the optimal solution. And the result would look something like this. You can see it's almost quite similar to the previous linear programming problem. We have different constraints regions in here, and because they are two-sided constraints, so that's why it looks like a window opening up in the middle that specifies the feasible region. And our optimal point is the bluest point in this single feasible window here that can be considered as the solution. Take some time and try to answer these questions for the quiz. And if we continue, while we can only plot the 2D contour by fixing one of the design variables, if we think retrospectively, we can actually create a slider for the C value so that we make it even more interactive. And then we use that slider to change the fixed xc value to see how that solution comes into place. Now, to set up an interactive plot, we'll have to first compute the objective and constraint values for a range of xc, which is the variable that we are fixing, and then we can store it in a sequence of frames where each frame will be like a snapshot of the contour plots, and then we can create a slider to move between the different frames. So here we have a helper function to compute for a particular xc value, what would the objective be like, what would the constraint value be like, and so on. Then we want to compute the data for the initial frame first, because that will be the first frame we plot as a placeholder. Then again, we create the objective contours, we add the constraints, also the optimum points. Then in here, this is where we're going to create the different frames for the xc value. So for xc range, which is a range that we've defined earlier of the possible values of xc, we want to first compute the values of the different objective function or constraint function, and then we want to append a new frame in it by updating the data of the contour and also the constraints as well. Then we can create a slider in here where we animate the different frames according to the position of the slider at that point. And then we can just define the sliders and add it to our figure. Now here, this is where the result is shown. You can see we have xc, the value of it, in a slider, and when you slide it across, you can see the plot will change. And very interestingly, we can see that our shaded regions actually move. So this means that for different value of xc, the plot will be different. And if we start from the initial position, xc being 1, you may not be able to tell instinctively, but actually if you toggle the GC shaded area, you'll see clearly that right now, although it doesn't look like there is any shaded or unshaded region, it actually covers all of your design space. So all of it is infeasible, so it's not a feasible solution. If you toggle it off, you can see that this is where the feasible solution would be if we don't have the third constraint. But right now, at this particular xc value, there will actually not be any solution here. But as we move across this slider, slowly and slowly, we have a shaded region that appear. Now in here, you can see the shaded region of GC actually moves towards that side. And now it's exposing some feasible region. So finally, we are having some feasible design points over here. And if we increase GC more and more, we actually expose more and more unshaded region. That is where we can find our solution. So you can actually understand why the solution we found earlier is the optimal solution, because it's the point where the GC constraint first moved to this point with a specific value, where it exposes a region where there could be feasible solution. And it is at this point where this particular position on the design space here would have the lowest value, because if you slide it across even more, you can see that the same point actually has a redder color to it. So it means that if you increase XZ more and more, although the unshaded region is still here, you can still find feasible solutions here, but the objective value or the cost will actually be increasing more and more. So this will not be the solution to your minimization problem. So what you want to do is that you want to go back to where it first started, exposing that point here, which is the value that corresponds to what we found earlier. And that's how you can make sense of an optimization problem, even if it isn't a simple 2D optimization problem. By including slider like this, you can then understand how this solution comes into play. Again, feel free to play around with this interaction and answer these questions so you can pick the correct answers in the upcoming quiz.